Before time, before space, before any law of physics we know, there was a state of infinite density and temperature. But what happens next? The answer unfolds within the very first fractions of a second. Imagine the universe at its very first possible moment, a state of existence so extreme that the laws of physics as we know them simply stop working. This is the Planck epoch, a realm of infinite density and unimaginable heat, a singularity that defies all logic and measurement. But what could possibly come next from such a chaotic, impossible beginning? The answer unfolds within the very first fraction of a second. A journey that begins with a temperature of 10 million trillion Kelvin. At this incomprehensible heat, the universe wasn't just a soup of particles, it was a single unified entity where all four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were indistinguishable from one another. This was a perfect symmetry, a period of ultimate simplicity before the complex cosmos we observe today came into being. But this perfect state couldn't hold, and the very first chapter of creation begins with a fracture in that unity. The first force to break away, peeling off from the unified whole, was gravity, a cosmic divorce that unleashed a staggering amount of energy into the nascent universe. Why is this separation so monumental for the story of everything that followed? This segregation at the 10:43-second mark, as the Max Planck Institute detailed in 2021, is theorized to have released an energy so vast it jump-started the universe's initial, explosive expansion. It marks the point where our modern understanding, rooted in Einstein's general relativity, meets a wall, demanding a new, unperfected framework of quantum gravity to truly comprehend the events that transpired. This profound shift set the stage, transforming a state of perfect unity into a dynamic, expanding reality we are only just beginning to explore. Before this cosmic force split away, all was one. In the next instant, the universe began to race toward its grand destiny. Here is the script for part 2, written in English, adhering to all constraints. Hold on. Let's rewind to a moment incomprehensibly brief, a mere whisper after the beginning. By the time the universe was just 10 to the power of negative 36 seconds old, something outrageous was about to happen. The force had already broken away, and now the cosmos itself prepared for a violent exponential leap that defies all terrestrial logic. This is the story of the ultimate speed run. Between 10 to the negative 36 and 10 to the negative 32 seconds, the universe didn't just expand, it inflated. According to data from NASA's WMAP mission, this period of cosmic inflation saw space stretch at a rate that vastly exceeded the speed of light. Think about that for a second. How can space itself break the universe's ultimate speed limit? The answer lies in the fact that it wasn't matter moving through space, but space itself that was ballooning outward, carrying everything with it. In less than a trillionth of a second, the universe grew by a factor of at least 10 to the 26th power. A region smaller than a proton was suddenly the size of a grapefruit, and then, in the next instant, something far larger than our entire observable galaxy. Who could possibly propose such a mind-bending idea? In 1980, a young physicist named Alan Guth at MIT was wrestling with a profound problem, a puzzle about why the universe looked so uniform. He realized that this incredible expansion was the only logical answer, and his theory, published in Physical Review D, elegantly resolved the mystery. But why was this runaway expansion so absolutely necessary for our existence? The answer to that is the key to everything. Without it, the universe would have been a chaotic, lumpy mess, collapsing back on itself before any stars could ever form. Inflation smoothed out the fabric of reality, making it flat and homogeneous. And then, as abruptly as it began, it ended. The energy that had been driving this phenomenal growth was transformed, and at 10 to the negative 35th second, something incredible happened. That energy condensed into the very first matter. Following Einstein's famous equation EmC², pure energy became particles. The first quarks and gluons, the fundamental building blocks of all future matter, were created from the fading fire of inflation itself. The stage was now set, but this newborn universe was still an unimaginably hot and exotic place. Imagine a universe filled not with stars and planets, but with a substance so hot and dense that the very building blocks of matter haven't formed yet. This is the quark-gluon plasma, a primordial soup that existed for just a fraction of the universe's first second. The temperature is so unimaginable that quarks, the fundamental particles that will eventually make up everything, cannot bind together into protons. It's a state of existence so extreme that you might think it can never be recreated, locked forever in the past. But what if I told you that scientists have managed to recreate this exact state of matter right here on Earth? To capture this ancient substance, researchers at the relativistic heavy ion collider at Brookhaven National Laboratory smashed together gold nuclei at speeds approaching the speed of light. These collisions generate a fireball of energy so intense that it briefly recreates the conditions of the early universe. But when they did this at the ALICE experiment at CERN's Large Hadron Collider, they produced something that shattered their expectations. They created a quark-gluon plasma with a temperature of 5.5 trillion Kelvin, which is over 100,000 times hotter than the core of the Sun. Yet, the most astonishing discovery was that this incredibly hot, dense matter behaves not like a chaotic gas, but as a perfect liquid with virtually no viscosity. This was completely contrary to what physicists had predicted, proving the universe's earliest moments were even stranger than we could imagine. The protons and neutrons that make up all matter didn't appear until the universe was about 1/1,000,000th of a second old. For that incredibly brief window, the entire cosmos was a glistening, almost frictionless fluid, a hidden secret of creation now unlocked in our laboratories. Now, after all that creation, a crisis emerged. Matter and antimatter should have been born in perfect symmetry, each pair destined to annihilate in a flash of pure energy. If that symmetry had held, the universe would have become nothing more than a shimmering sea of radiation, a cosmic ghost town with no stars and no planets. Instead, for every billion antiprotons, there was a billion plus one protons. That is the staggeringly delicate imbalance, a margin of 1 in a billion, that makes our existence possible. The Large Hadron Collider at CERN has been hunting for the source of this asymmetry, and its LHCb experiment has measured the behavior of particles and their antimatter counterparts with remarkable precision. Yet a complete explanation for why matter won this cosmic lottery remains one of the most profound unanswered questions in modern physics, according to Scientific American in 2020. How did such a tiny difference emerge from such a perfectly balanced beginning? The survival of every atom you are made of hinged on this fragile tipping of the scales. By 1/10,000th of a second after the Big Bang, the universe had cooled to 1,000,000,000,000 degrees Kelvin, a temperature so extreme it defies everyday intuition. At this moment, the basic building blocks, protons and neutrons, were emerging from the seething energy, but they didn't form in equal numbers. Because a neutron is about 0.1% heavier than a proton, nature's accounting tipped the scales, producing roughly 6 protons for every single neutron. This tiny mass difference, measured by the National Institute of Standards and Technology in 2019, dictated the future composition of everything we see around us today. So what happened when these particles began to collide? Starting 1 second after the Big Bang, a process called nucleosynthesis took over, lasting just 3 short minutes until the universe cooled below the threshold for fusion at around 3 minutes and 46 seconds. During this frantic window, protons and neutrons fused into helium nuclei, locking about 25% of the universe's mass into that element, leaving the remaining 75% as hydrogen. The heavier elements, carbon, oxygen, iron, were not forged here. They had to wait billions of years for stars to cook them in their cores. Yet this simple recipe of hydrogen and helium, created in those 3 minutes, accounts for over 98% of all baryonic matter observed today, a fact confirmed by the Planck satellite. When astronomers look at young galaxies and measure their helium fraction, they find that same 25%, a verification so clean it stands as one of physics' greatest triumphs. The universe's entire elemental story was largely written before you could blink, and we still carry those proportions in every atom of our bodies. Picture the universe before its 380,000th birthday. Not a starry void, but an endlessly dense fog, a cosmic steam so thick that no beam of light could travel more than a few steps before bumping into a free electron. For hundreds of thousands of years, the cosmos was literally opaque, a glowing cloud where particles of light were trapped in a ceaseless, chaotic pinball game with no escape. But then came the critical moment when the expanding universe cooled to about 3,000 Kelvin, and the physics changed forever. At that temperature, electrons finally slowed down enough to be captured by protons, forming neutral hydrogen for the very first time. With those electrons finally locked into atoms, the photons were suddenly free, all 380,000 years of trapped radiation bursting loose in a single universe-wide flash of liberation. That ancient flash is still traveling toward us today, and we call it the cosmic microwave background, or CMB, the oldest photograph of existence ever taken. Here is the part that shocks people. That perfect cosmic snapshot was accidentally discovered through a persistent, irritating hiss of static. In 1965, Arno Penzias and Robert Wilson at Bell Labs in New Jersey had a radio antenna that would not stop picking up a low-level noise, no matter what they did. They checked every wire, every connection, every piece of equipment, and even discovered a family of pigeons had nested inside the antenna, leaving a thick layer of droppings that they dutifully cleaned away. But the hiss refused to vanish, still whispering from every direction of the sky at exactly the same intensity. It was Robert Dick from Princeton who heard about their problem and realized the truth. Those two engineers had just stumbled upon the leftover glow of the Big Bang itself, the exact signal his own team was scrambling to find. The mysterious nods was radiation that had been traveling through space since the universe was a mere 380,000 years old, and it confirmed the Big Bang theory in one decisive, almost accidental blow. But what makes this ancient light truly captivating are the tiny imperfections hidden inside it. Fluctuations so subtle that they mess with our sense of scale. When NASA's COBE satellite first measured the CMB in 1989, led by John Mather and George Smoot, it found a perfect blackbody spectrum at 2.725 Kelvin, a discovery that won them the Nobel Prize in Physics in 2006. At first glance, the CMB looks perfectly smooth, but look closer and you find temperature differences of only 1 part in 100,000 tiny ripples across the sky. Those microscopic wrinkles are not imperfections at all. They are the seeds of everything, the gravitational blueprints from which every galaxy, star, and planet would eventually grow. Without those minuscule variations, the universe would be a featureless, eternal sameness, and we would not exist to ask the question. Then, in a triumph of precision, the European Space Agency's Planck satellite measured that ancient light with such accuracy that it pinned the universe's age at 13.8 billion years, give or take a mere 20 million, a feat of cosmic bookkeeping that feels almost arrogant. So, the next time you look up at a clear night sky, remember that you are seeing only the tip of creation's story, the visible part of a timeline that began with an opaque fog and a trapped flash. We have in our telescopes a faint hiss of microwave static that is direct evidence of our own birth, a baby photograph of a universe just beginning to settle into its long, patient sleep. But here is the thrilling part. Once that light was released, the universe entered a dark, silent era, waiting for something new to ignite the void. What happened next, when the first stars finally awakened, is one of the most dramatic chapters in all of cosmic history. Imagine the universe after its first 380,000 years, a dark, featureless fog of hydrogen gas with no stars, no galaxies, no light to break the silence. This is the cosmic dark ages, a period that stretches on for roughly 100 million years according to NASA, a long, quiet night before the first dawn. How do you even begin to visualize an era where absolutely nothing shines, where the only actors are neutral hydrogen atoms drifting in the void? But this emptiness was not eternal, for gravity was quietly at work, pulling at the denser patches of that primordial mist. Around 100 million years after the Big Bang, the first stars finally ignited, and their birth was on a scale we can barely comprehend. These were population 3 stars, colossal giants that weighed hundreds of times more than our Sun, burning brilliant blue and living fast, dying young in just a few million years. Their arrival didn't just add light, it fundamentally changed the universe by flooding space with intense radiation that stripped electrons from the surrounding hydrogen gas. This process, known as reionization, marked the end of the Dark Ages and transformed the cosmos from an opaque fog into the transparent, structured place we see today. So when you're planning a video about this epic transition, how do you even begin to condense it into a clear and engaging story? The key is to build a visual timeline, an infographic that guides your audience through these unimaginable timescales without losing them in numbers. First, you need to pick just 5 major milestones that define the whole narrative. The Planck time at 10 mseconds, the cosmic inflation at 10 femtoseconds, the quark-gluon plasma at 10 mseconds, nucleosynthesis at 1 second, and the release of the cosmic microwave background at 380,000 years. For each one of these moments, you'll want to find a single powerful symbol or number that captures its essence, like the insane temperature of 10 cubic Kelvin for the Planck era, or the fragile 1 to 1 billion ratio that explains why we exist at all. But to make the timescale truly click, you have to switch from a normal linear graph to a logarithmic scale, because plotting 10 seconds on a straight line would make it look practically the same as 0. This way, you can visually represent the sheer difference in scale between each cosmic epoch, showing just how much happened in the first few minutes compared to the millions of years that followed. To bring it all together, link each milestone to a modern experiment that proved it, the LHIC COBE or the Planck satellite, showing that this isn't just abstract theory but a story we've validated in labs. And finally, the most powerful tool is to end on an open question, something like, but what came before this all began? To spark that feeling of wonder and drive your viewers to seek out more. These early stars were the spark that lit the universe, but their light also set the stage for the next great transformation. For roughly 400 million years after the Big Bang, the universe sat in a quiet, dark state, filled with nothing but neutral hydrogen gas left over from the recombination era. Then, something remarkable began to stir, as gravity slowly pulled that gas together into the first colossal structures. The very first stars and galaxies ignited, and their intense ultraviolet light started to rip electrons off those hydrogen atoms once again. This dramatic transformation, known as the epoch of reionization, unfolded between 400 million and 1 billion years after the Big Bang, according to the European Space Agency's Planck mission. Where did all this ionizing energy come from? The source wasn't a single dramatic event, but the cumulative firepower of countless young, massive stars blazing inside the earliest proto-galaxies. These infernos were so hot that they flooded the surrounding space with high-energy photons, turning the once-neutral fog back into a sea of free electrons and protons. Imagine the universe's very first sunrise, not over a planet, but over the entire cosmos, burning away the haze. This phase transition fundamentally redefined what the universe looked like, turning it from an opaque shroud into a transparent one where light could finally travel freely in every direction. This wasn't just a simple reheating, but a fundamental change in the state of matter that governed how the cosmos evolved. As the neutral hydrogen became ionized, it allowed the newly forming galaxies to emerge from the shadows that had previously hidden them from view. The very structures we see today owe their existence to this cosmic renaissance, which cleared the way for the large-scale structure of the universe to develop. Without this powerful reionization process, the early light from the first stars would have been trapped, and the universe might have remained a featureless, dark expanse. It was this dramatic shift, powered by the birth of the first galaxies, that set the stage for everything that followed. What tools would humanity eventually build to look back and capture the faint echoes of this ancient transformation? For decades, the Big Bang Theory rested on a surprisingly small set of pillars, but modern science has turned it into a fortress of evidence. The data from the Planck satellite, for instance, has not only confirmed Edwin Hubble's 1929 observation that galaxies are receding at speeds proportional to their distance, but has also refined the Friedmann equations that describe an expanding universe. Yet the most astonishing confirmation came from a satellite built to measure static, a mission that redefined cosmology itself. The COBE satellite, led by John Vather and George Smoot, revealed in 1990 that the cosmic microwave background is a perfect blackbody spectrum, a discovery that earned them the 2006 Nobel Prize in Physics. How fitting is it that a $100 million mission was launched to measure a faint hiss that turned out to be the echo of creation? That faint hiss contained tiny temperature ripples, the very seeds of every galaxy we see today. But the chase for confirmation did not stop there, as physicists turned their attention to a far more elusive quarry. The BICEP and Keck collaborations have been scanning the sky for primordial gravitational waves, the hypothetical ripples in space-time that would be the direct signature of Alan Guth's inflation. While that detection remains unconfirmed, the search itself underscores how far we have come. Have we forgotten the humble origins of this grand narrative? It was Georges Lemaitre, a Belgian priest, who first proposed the primeval atom in 1927, a concept that Fred Hoyle mockingly named the Big Bang on BBC Radio in 1949. Today, even the James Webb Space Telescope adds its weight to the story by observing distant Type Ia supernovae, confirming that the expansion of the universe continues to match predictions. The theory has survived every test, but each answer has only deepened the mystery of what lies beyond our knowledge. Here is the script for Part 10. Dark Matter and Dark Energy, written in English, following the outline and incorporating the specified facts and guidance. We've traced the universe from a singular point to a sea of particles, but here's the uncomfortable truth. Everything we've talked about so far, every star, every galaxy, every atom in your body, accounts for a mere 5% of what's actually out there. According to data from the European Space Agency's Planck satellite in 2018, the universe we can see and touch is just a thin veneer on something far stranger. The remaining 95% is split between two invisible entities we barely understand. About 68% is dark energy, driving the universe's expansion apart, and 27% is dark matter, holding it all together. So, what are these cosmic ghosts that have been with us since the very beginning? The leading models suggest that dark matter isn't some exotic form of normal matter, but a new kind of particle born in the intense heat of the early universe, right after inflation. The prime suspect is the WIMP, or weakly interacting massive particle, a theoretical particle that passes through ordinary matter, a ghost, interacting only through gravity and the weak nuclear force. To catch one, scientists have gone to extraordinary lengths, building detectors deep underground to shield them from cosmic noise. The Sinon 1T experiment in Italy, for instance, uses a tank holding 3.2 tons of liquid xenon, waiting for the faint flash of light that would signal a WIMP collision. But so far, the silence has been deafening, with no clear signal ever detected. But what if dark matter isn't a heavy particle at all? What if the answer is something almost impossibly light? A particle so ethereal it was first proposed to solve a completely different problem in physics. If the WIMP remains elusive, a leading alternative is the axion, an ultralight particle first predicted by string theory and field theory. These particles would be so numerous they could permeate all of space, and experiments like ADMX at Fermilab are now trying to detect their faint conversion into microwave photons in a strong magnetic field. The hunt has only just begun, and the possibilities are as mind-bending as the cosmos itself. So how do we make sense of this for a classroom? Let's build a 10-minute presentation on the journey from the Big Bang to us, using guidance inspired by CERN, NASA, and ESA. First, open with a question that hits home. How many elements in your body were created in the Big Bang itself? The answer is just 2, hydrogen and helium, which make up about 98% of the universe's mass. Then use a simple analogy. Think of the first 3 minutes as baking a cosmic cake, where the ratio of ingredients, like the 25% helium, is locked in from the start. Show the Planck image of the cosmic microwave background as the universe's baby picture, explaining that its color variations, differences of just 1/100,000th of a degree, are the seeds of all future galaxies. Finally, bring it all together with that humbling truth. We are made of the 5% we know, while the other 95% remains a mystery. The universe is 13.8 billion years old, and we still know so little about almost all of it. So, what came before all of this? It is the most natural question to ask, and it is the one science still cannot answer with certainty. The mathematics we use to describe the universe breaks down completely at the moment of the Big Bang, leaving us with a wall we cannot see beyond. Many physicists now treat time itself as a dimension that simply begins at that point, making the concept of before as meaningless as asking what lies north of the North Pole. Yet this has not stopped some of the greatest minds from proposing bold ideas, such as a cyclical universe that expands and contracts forever, suggesting our Big Bang might not be an absolute beginning. Others have even suggested that the universe could have arisen from literally nothing, because the total energy of everything, when accounting for the negative energy of gravity, might perfectly add up to 0. It is a staggering thought that the quantum vacuum itself might be capable of birthing entire cosmos. The questions only become stranger when you peer closer. The early universe, for all its violence, was governed by quantum mechanics, leaving a statistical fingerprint of random noise imprinted on the cosmic microwave background. Data from the ACT and SPT collaborations now hint at the possible existence of a mysterious dark radiation, extra particles that would push the effective number of neutrino species beyond the standard model's prediction of 3.046. If confirmed, this would be a direct signal of physics we have never seen before, forcing us to rewrite our textbooks. And what about the neutrinos themselves, born in the first second when the universe cooled to 10 billion degrees? They are still flooding the cosmos, a faint cosmic neutrino background that experiments like Ptolemy are desperately trying to detect. These elusive particles are so low in energy and interact so weakly that observing them represents one of the greatest technical challenges in all of modern astrophysics. Then, in 2023, the James Webb Space Telescope threw a new wrench into the works. It spotted galaxies like Jada's GSZ 13-0, which appear to be surprisingly massive and mature just 300 million years after the Big Bang, a time when the standard model says they should have been small and chaotic. This unexpected finding suggests that structures may have formed far faster than our current theories can explain, and it has cosmologists scrambling to re-evaluate their models. The existence of these two early galaxies makes us wonder if we have fundamentally misunderstood the rate of cosmic evolution. We are left with a universe that is far stranger and far more complex than our equations can fully capture. Every answer we uncover seems to open a dozen new questions about the fundamental nature of reality, and the final punchline-worthy truth is that the more we learn, the more we realize how little we actually understand about the grand story we are a part of. We began with a singularity, a state of infinite density and temperature, where every law we know collapses into a single point. From that impossible beginning, the universe expanded, cooled, and transformed through a sequence of events so precise and so violent that their echoes still shape our existence. In the first fraction of a second, inflation stretched space itself, seeding the cosmos with the fundamental particles that would become everything we see. The cosmos then spent its first 3 minutes forging the lightest elements, a process that locked in roughly a quarter of all ordinary matter as helium, a ratio that still holds today. After hundreds of thousands of years, the fog of plasma finally cleared, releasing the cosmic microwave background, a faint snapshot of that ancient moment that we can still capture. The first stars then ignited, ending the cosmic dark ages and beginning the slow process of building galaxies and planets. But for all we have learned, the story remains profoundly incomplete. We are left facing the question of what existed before time itself. And we must admit that over 95% of the universe is made of dark matter and dark energy, substances we cannot yet grasp. Our very existence, too, hangs on a fragile asymmetry, a cosmic imbalance where for every billion particles of antimatter, there was one extra particle of matter, and that 1 part per billion margin is the only reason any of this exists. The Big Bang was not an explosion in empty space, but rather an expansion of space itself, a concept that defies our intuition and reshapes our understanding of everything around us. Indeed, the total energy of the universe may be zero, with the positive energy of matter balanced perfectly by the negative energy of gravity. Now, the James Webb Space Telescope is sending back images of galaxies that appear too mature, too structured, for a universe so young, challenging our models and hinting at mysteries we have yet to identify. So what comes next? We are only beginning to unravel the greatest story ever told, a narrative written in the light of ancient stars and the faint hum of background radiation. Let us keep watching, keep questioning, and keep exploring the origins of everything.